Let's wait for 2 3 minutes and then we'll start. Okay, we can start. Okay, so this is week 5, problem solving sessions on the mathematical methods in physics 1. So today my plan is to actually in week 5 content, if you look at the NPTEL, the course is designed uh, in such a way that in the week 5 to week 8, generally the differential equations have been solved, and particularly the ordinary differential equations. We are not going to discuss much about the partial differential equations. So this particular content, this particular week's content, I would rather say, is mostly based on the ODEs, the ordinary differential equations. So we'll see that what is the order or what you call as the degree of differential equations, how to solve the linear first order differential equations. Then we will go for the, the equations of the second order differential equations with constant coefficients, how to solve them. Particularly, this week is focused on the homogeneous equations. Then again, a question comes that what is homogeneous equation, what is inhomogeneous equation. We will talk in details all these things. Of course, it is already being given, so it will be good revision of those who will be looking at this particular lecture. So, with each of the introduction of different ways of solving, I have tried to put some examples by some numerical questions will be there, and we will solve those. That will clear our concepts. Okay, so this is the major thing. So it will be week 5 will be based on the ODEs, which is nothing but the ordinary differential equation. Okay, so this is the main theme of this particular week, and today I will be trying to give a an introduction of all these things, and it will be good revision as well as do some numerical questions. So before going into the details of the ordinary differential equation, let us know that what is a differential equation. So let me write down the definition of a differential equation. Simple definition is that the differential equation is that equation which involves differential coefficient. For example, what are the differential coefficient? Simple derivatives like dy dx or dx dy or whatever, or d2x dy dy2 and anything. Okay, so differential coefficients. This is the simple definition of, or very common definition of a differential equation. This differential equation, these differential equations are of two kinds. One is what we will discuss today, the ordinary differential equation, and mostly we will not discuss this, which is the partial differential equations. Partial differential equations, much more useful in electromagnetism. People use the electromagnetic wave equation. So that are nothing but the partial differential equations. And there is another way which we will be discussing most of the times. We generally see it in the simple harmonic oscillator or something, which is nothing but the ordinary differential equation. Okay, so both has its own importance. We will see that what is the difference between this ODE and the PDE. So what is ODE? I have already written. It is ordinary differential equation. This is partial differential equation. Okay, partial differential equations. Okay, so what is the difference? So ODE is generally it will be consisting of, it consists of derivatives with respect to a single dependent variable. Okay, so it will consist of, what happens is that these derivatives are nothing but an operator. This operator will be on a particular function, say y. Let this y be some kind of a dependent variable which is depending on an independent variable x. So if y is dependent on x only, one variable, single variable, then that is the ordinary differential equation. Whereas if it is depending on, say, more than one variable or more than one dependent variables, then you will call that as an as a partial differential equation. So this is the major difference. So partial differential equation will be consisting of, it consists of derivatives with respect to more than one, right? More than one independent variable, right? So these are the two things. Okay. Yeah. So these are the two important things. Next is about, we'll be talking about the order and degree of differential equation. Order and degree of differential equation. Okay, just a minute. Okay, so fine. So order and degree of the differential equation. There is one mistake I have given here. This is single independent variable. Okay, so x is an independent variable. So derivative will be dy by dx. It's a total derivative. Okay, dy by dx. So y is a function of x only. So dependent variable y is a function of a single variable. So derivatives are involving single independent variable. But here it can be del x, can be del y, and higher orders as well. Okay. So more than one independent variable. So it's not dependent, it will be independent variable. Fine. Order and degree of a differential equation. So let's write what is order of a differential equation. So this order is the highest order the highest order derivative present in the differential equation. Differential equation. I will give the example. Differential equation. Right? And what is the degree? So the definition of a degree is it is the power of the highest order. See, just now we have discussed about the order of a differential equation. Just look at it. The degree is also dependent on the definition of the order. So it is the power of the highest order derivative. Okay, highest order derivative term in the differential equation. All right. So these are the definitions of order of a differential equation and degree of a differential equation. So what are the difference? Difference is that for the order, definition of order is the highest order derivative which is present. That's all. Degree is you identify the highest order derivative and see the power of that highest order derivative. That is the difference, right? So let me give an example. So let's say 1 plus dy dx whole square and its cube, suppose that is d2y by dx to whole square. This is what is given. Okay, so now you can clearly see that the highest order derivative which is present is the order 2, right? This is the order of derivative dny by dxn. This is the order of the derivative, right? Order of derivative. So your here the order is 2. Now what will be the degree? The degree is also 2. Correct? Because the highest order derivative is power. Correct? Simple, if you just take dy by dx plus y is equal to say 2x. Okay. Then what will happen? What is the order and degree? So order will be the order highest order derivative. So derivative highest order is there. Right? So order will be 1. What about the degree? It's power. The highest order derivative power, which is what? 1. So this is how you generally find out the order and degree. So these are the definitions of the order of a differential equation and the degree of a differential equation. Right? So this is one of the concepts which needs to be known before going to the next couple of things. Okay, the immediate next thing is the linear differential equation. Okay, what is a linear differential equation? Once we deal with this, once we see the definition of the linear differential equation, immediately the question will arise, then what will be the nonlinear differential equation? So we will see that. Okay, let us first define what is a linear differential equation. Okay, so if the definition is if every dependent variable and its derivative. So what is a dependent variable? Suppose y is a dependent variable on some independent parameters x. Okay. So if every dependent variable and its derivative occurs in first degree only and no product of dependent variables and its derivatives are present. Okay, so actually, this definition is showing you certain conditions, right, to have the linearity. If these conditions are not satisfied, any of these conditions are not satisfied, then it becomes the non-linear differential equation. So what is being said here? If every dependent variable, say some y of ax, y which is a function of x, which is a dependent variable, okay, this is a dependent variable, and its derivative, so dy by dx, occurs in first degree. That means order of the highest derivative should be 1. Okay, this is the meaning of this. And no product of the dependent variables and its derivatives. Right? So y square or y dy by dx, these things should not happen. Right? Also, this y, this function, should not be non-linear. It should not be. Okay, should not be non-linear. This is also another condition. Okay, so this, then only we can say that a differential equation is a linear differential equation. So what is an example of that? So let's see. Uh, Let us see two examples. One is d2z by dt2. Okay, people can say it d square z by dt square. Anyway, it is fine. People, there are two ways of representing this or saying this: d2z by dt2 or d square z by dt square. Anything is fine. Okay, so d2z by dt2 minus 5 dz dt plus 7z is equal to 0. This is one of the example of a linear differential equation. Okay, this is a linear differential equation. Why is a linear differential equation? See, z is the dependent variable here. Okay, z is a dependent variable which is dependent on t, right? Which is independent. This is independent. Fine. So z is a dependent variable. Do you find the product of the z with another dependent variable? No. Do you find that there is a product of the dependent variable and the derivative of the dependent variable? No, we have not found. Next, do we find that the degree of the dependent variable derivative is more than 1? No. So you have the highest order, d2z by dt2, its power is 1. Hence, it is a linear differential equation. Okay. Next, example 2 is suppose x square dy by dx plus x square y is equal to sin x. This is also a linear differential equation. Why? Because here y will be a dependent variable. Okay, y is the dependent variable on x. So x is independent. Clear? Now, question: do we see that there is a nonlinear functionality of the dependent variable? No. There is a nonlinear function sign, but it is on the independent variable. So it's fine. Okay, number one. Number two is that do we find, is there any product of the dependent variable with itself or the dependent variable with the derivative of the dependent variable? No. I couldn't find any term representing y dy by dx or y square. No, it's not there. Fine. Next is, do we find the degree of the highest order derivative is more than 1? No. This is 1. This is the highest order derivative is 1. Then this shows that it is also a linear differential equation. Fine. These are the two important examples. But okay, we talked about the linear differential equations. Now let us say about the non-linear differential equation. Simple. Non-linear differential equations, if I write the example, you will understand very easily. Just those equations which will not follow these linear conditions. What are those conditions? That if every dependent variable and its derivative occurs in the first degree, so your degree should be one, number one. Number two is that there must not be any product of the dependent variables and its derivative. So there must not be any term which consists of y times y or y dy by dx. Okay, this should not happen. And there must not be any non-linear function. Simple. So we have seen that in these two cases, these are valid. Let's see for the non-differential equations how we can categorize them. One of the examples of the non-linear differential equation is, say, suppose this x square dy dx plus x square y is equal to sine y. Okay, this is a non. I'm calling this as a non-linear differential equation. Why? Question is why. Let's check one by one. Do we find that the degree of the differential equation is more than 1? No. The highest order derivative is dy by dx. Its degree is 1, right? Its power is 1. So that suggests that this is fine. This holds the linearity still. Next, do we find any product of the dependent variables as well as the derivative of the dependent variables? No. We cannot find any term having y divided by dx because y is the dependent variable here. X is the independent variable. Clear? So it is not there. Still holds the linearity. But the only problem is that you have this sine y, which is a nonlinear function of y. That's why this nonlinearity makes this differential equation a nonlinear differential equations. Otherwise, it's absolutely fine. Okay, this is number one. Second is, let's take an example of the second, x square dy dx, simple equations, x y square is equal to x. Everywhere it is fine. Degree is 1, no problem, but product of the dependent variable with itself. So product of dependent variables can be seen. So that's why it is not doing. Okay, otherwise everything is fine. Third is dy by dx square plus xy is equal to 1. So you can clearly see that the degree is greater than 1, hence it is not zero. That's all. So these are the couple of things which one must note. Remember again, if you find any differential equation consisting of this is also be considered as non-linearity. Okay. So generally we find that in the Navier-Stokes equation, those who are from the fluid mechanics background, there in the Navier-Stokes equations, you find that you have a term like u delta u by delta x. Okay, so you can see that u, which is the dependent variable, there is a multiplication of, although this is a partial differential equation, so not to worry about that. This is I'm showing. Okay, so u delta u by delta x, this kind of term comes, and that's why it makes the equation non-linear and hence difficult to solve. Fine. So this is all about the linearity and the non-linearity of the differential equations. Fine. Let's go one step forward. So you have a linear differential equation. Suppose this is a linear differential operator. Y of x is suppose f of x. Alright. So this is the thing. So we can write this as a naught y plus a1 y dash, the derivative, a2 y double dash, so on up to any term we don't know, this is equal to b. Okay. Now, if in this f of x is equal to 0, there is no forcing. So this is actually in physics, it will be the forcing, some kind of a forcing parameter. Okay. If this fx is 0, then we call the differential equation as a homogeneous differential equation. Differential equation. But if this f of x is not equal to 0, this becomes simple inhomogeneous. All right. So this is another part. Okay. So then how do we write the nth order differential equation? Very simple. Nth order differential equation can be written as this an of x. It can be constant also, it doesn't matter. dny dxn. Nth order derivative should be there. That's all. N minus 1x dn minus 1y by dx n minus 1. So on it will go. And finally, you end up here a1 of x dy dx plus a naught of xy that is equal to b of x. This b of x is the quotient. If it is becoming 0, then you will find that that will be a homogeneous differential equation. Fine. So these are the couple of things. Okay. Next, we go for linear first order differential equation and try to see how to solve. Okay. Linear first order differential equation. Okay. This is the next topic, the linear first order differential equation. We'll see that how to solve the linear first order differential equation. So one by one we will see. Okay, fine. So how to represent this? Dy dx should be equal to some function of x comma y. All right, this is your linear first order differential equation in a generalized sense. Now what we will do is that sometimes it may happen in your question that this f of x on x comma y becomes separable. Means you can write it in terms of function of x and sometimes function of y. So you can write this as sum minus p of x divided by q of y. It doesn't matter whether you keep this minus or not. It doesn't matter really. Okay, you can put it plus. That's absolutely fine. So this can happen sometimes, not always. Okay, there are ways when this kind of thing will not work. Okay, so we will see one by one. So dy dx is minus p of x divided by q of y. Clear? This is done. Next, what we will do? Just the integration. That's all. Q of y dy, and this will give you minus p of x dx. No requirement of this minus sign. You can remove it. I have just given on my own. That's all. Y1 to y2 and x1 to x2. You integrate and you will find an equation of y in terms of x. Okay. So this is the solution of the differential equation. This process, when you can write when dy by dx can be written as sum minus of px divided by qy. We call this method as variable separable method. Method of variable separation or variable separable method. Okay, so this is one of the ways you can solve. One of the examples in physics for this variable separable method is the radioactive decay. Radioactive decay. So you know that in the nuclear reactions there are several nuclear reactions where initially you have some content of some the constituents like N, okay, radioactive sample which is N, and slowly with time it decays exponentially. So how do we get that? So for that, it has been found out that the radioactive decay, or I would say, it is actually the observation which, yeah, the observations tell you that the rate of nuclear decay or this reaction decay of what? Decay of the radioactive sample. Decay of the radioactive samples is proportional to the remaining number of atoms or samples, whatever. Okay. So how do we represent this? D and dt, the rate of radioactive sample decay with respect to time is proportional to n. And we can see that there is a negative sign. This negative sign is that once there is a radioactive decay, the rate of decay is being said, right? So rate of decay, that's why there is a negative sign. So samples will decrease as the radioactive reactions. So look at this. You can write this as dNdt is equal to sum minus lambda coefficient, okay, proportionality constant lambda times n. So this becomes a differential equation, and this becomes a function of time. Okay, so this is also a function of time. So you can clearly see that here the method of variable separation can be used. Okay, so variable separation method can be used, right? Variable separable method can be used. So we can write dnt by n of t is nothing but minus lambda d. So you can completely separate out the time component on the right hand side, the n component in the left hand side. And you start with n naught and finally come at n. And this at zero time the initial samples is n naught, and at some time t, this becomes n of t. So what is this integration? This will be log of n from n naught to n, and this will be minus lambda t. That's all. All right. So now this becomes log of n by n naught. This is equal to minus lambda t. So n by n naught log on that side, if you go, this becomes an exponential. So n of t is nothing but the initial sample times e to the power minus lambda t. So this gives you an exponential decay. Okay. So the nuclear reaction, when there is a decay, the radioactive decay, it happens exponentially. So this is of n of t, this is n naught, and with t time, this is how it goes. Fine. So this is how the variable separable method works, and this is one of the example of the physics of where the variable separable can be used. All right. So one another question, which is somewhat a tricky question. Let us solve that, and then we can move to another method of solving the first order linear differential equation. Okay, so let's try another question. So this question is little bit tricky. It has been given that dy dx is equal to 4x plus 6y plus 5 divided by 3y plus 2x plus 4. This is how a function is being given or the differential equation is being given. Now you have to solve it. Okay, so what we do is here is that, so it's a tricky question as you can see. What we will do is that see, this is 4x plus 6y, right? Can we write this as 2 times 2x plus 3y? Yes, we can write plus 5 divided by, in the denominator, you can see that 2x plus 3y already is there, and there is a plus 4. Now what we do is that we just simplify it and write let v is equal to 2x plus 3y. Okay. What about dv dx? This will be 2 plus 3 dy dx. Alright, this we can write. Okay. And then what will be dy dx? Dy dx will be what? Dy dx will be 1/3 of dv dx minus 2. Fine. This can be written. So dy dx, therefore, we are writing this dv dx minus 2. Also, dy dx is this. So in terms of v, can we write this as 2v plus 5 divided by v plus 4? Yes, we can write. Solving further, we get dv dx minus 2. This becomes 3 times 2v plus 5 divided by v plus 4. Further, let me go step by step. This becomes dv dx is equal to 3 times v plus 5 by v plus 4 plus 2. solve the right hand side properly, and you get 3 2b plus 5 plus 2b plus 4, which gives you 2b plus 8 divided by b plus 4. All right, this is done. Almost we are converting it into the linear or this variable separable method. You can see that on the right hand side, mostly all the terms are in V, whereas in the left hand side, you have dVdx. So you can clearly see that variable separable method can be used here. Fine, let's sort further. This becomes 3 to the 6 plus 2, 8V, 15 plus 8, 23 divided by V plus 4. This becomes the final thing. Okay, now what we will do is that instead of solving like this, let's do dx by dv. Just reciprocate this derivative. You get what? V plus 4 divided by 8v plus 23. Now, some little bit of manipulation we will do dx dv. I would not say manipulation, this is the arrangement I will do. Okay, so can we write this 1 by 8, 8v plus 23 plus 4 minus 23 by 8? Look, why have I done this? Because in the denominator you have 1 8v plus 23. I want it intentionally. So if you do that, you can clearly see that you will be getting v plus 4 here. Simple, it's easy. You can clearly see that. Okay, so once you get this, you can still write this as dxdv is equal to 1 by 8, 8v plus 23, 8v plus 23 can be chopped off. This becomes 9 by 8, 8v plus 23. That's what you get, correct? So on the left hand side, just keep the dx. On the right hand side, you multiply this particular expression 8 times 8b plus 23, this one, with dv and just solve it. This is the variable separable method. So integrate it on both sides. So this becomes x plus c, some constant, because you are not giving the limit of the integration. These are improper integrals, so you have to add some constant. This becomes b by 8. This becomes 9 by 8 times 8, because this also has to be differentiated. Log of 8v plus 23. All right. Further, solve it. X plus c. This becomes v by 8 plus 9 by 64 log of. Now v, I will put out this thing 2x plus 3 by 2. And once you do everything, you get 16x plus 24y plus 23. That's all. Okay, so finally, this is also a final expression, but you can further solve it because here also v is there. You can change that. Finally, we'll get 3y minus 6x plus 9 by 8 log of 16x plus 24y plus 23. That is equal to 8 times c. So this is the final solution of the question which we have done. So a little bit tricky, but this is an interesting question of the variable separable method. Fine. So we have looked into one of the methods to solve a linear first order differential equation, which is variable separable method. Not always you can convert it into a variable separable method. For that, we will now check another method to solve the linear first order differential equation. Okay, another way to compute the linear first order differential. So technique, another technique for solving linear first order differential equation is that suppose you have the differential equation like this: dy dx plus px of y is equal to qx. So in no way you can, maybe you can, but most of the times you might not convert this into a functional form of px divided by qy, what we have seen in the earlier case, right? For this kind of equation, you require integrating factor. So how to do this? So you define an integrating factor. Okay? You define an integrating factor. I will call this if as exponential to the power minus, okay, this p of x dx. This is how you write it. Okay, I'm sorry, this will be plus. Okay, px dx. Whatever is with y. Remember, the equation, the differential equation should be of this form. Remember, if it is of this form, then only we can use this. Okay, so the integrating factor is this. Now, for the solution of this differential equation, we will write this as y times the integrating factor is equal to integration q of x, the integrating factor dx plus some constant. Okay, this is how we write it. So so the final expression y times integration of px dx will be equal to qx e to the power p of x dx, again dx plus c. This is how the solution will be. Okay, let's try some questions based on this. So one of the questions is that x plus 1 dy dx minus y is equal to e to the power x plus 1 square, right? So what we will do is that, see, we have to convert it into this form. This form should be there. That means with the derivative there must not be anything. There will be some function of x only multiplied with the y, and on the right hand side you can have another function of x. It can be constant also. Doesn't matter. Okay, but here we can see that already there is a function which is multiplied with dy dx. We don't need that, right? So we divide by x plus 1 to make it into that kind of a differential equation. So what we'll do, if I divide dx minus 1 upon x plus 1 y e to the power x plus 1 whole square divided by x plus 1. So this x plus 1, this x plus 1 goes. So final equation becomes dy dx minus 1 upon x plus 1 y is equal to e to the power x plus 1. Alright. So now you can see that to the right hand side it is only a function of x. In the left hand side with y there is a function of x, and with the derivative there is nothing, only 1. Fine. This is now the converted differential equation. Now we can solve it using the integrating factor method. So what will be the integrating factor? The IF, the integrating factor is what? Exponential to the power integral p of x, including this negative sign. So it will be minus 1 upon x plus 1 dx. What it will be therefore? E to the power minus log of x plus 1. Correct? So what it will be therefore? It will be e to the power log of x plus 1 inverse. So e and log are reciprocative or inverse kind of a thing. So it will be 1 upon x plus 1. So x plus 1 inverse. Okay. So 1 upon x plus 1 will be the integrating factor for this particular equation. Then what will be the solution, as I have already told? So the solution will be y times the integrating factor 1 upon x plus 1 is equal, on the right hand side you have the qx, which is e to the power x plus 1, the integrating factor 1 upon x plus 1 dx plus some constant c, because this is improper integral, that's why the constant is required. This x plus 1, this x plus 1 goes, so y upon x plus 1, this will be equal to This is EXGX, which is nothing but E plus C. So y will be equal to x plus 1 e to the power x plus c times x plus 1. This is the final solution of the differential equation, this linear first order differential equation. Alright, now how to find out the C? If this is your question, then you need some initial conditions. Like for x is equal to some value, what will be the value of y? Okay, if for a value of a, y is given, then C can be found. Alright, so this is how the differential equation can be solved. Fine. Let's see next is the orthogonal trajectories. This is another concept which is interesting actually. Let me directly go to the next page. So the next concept is orthogonal trajectories. There's a good application of physics in this. You can clearly see when I will write some examples. So these orthogonal trajectories, so what happens is that, what about these orthogonal trajectories? What are those? So it is nothing but two families of curves are such that every curve of either family, okay, either family cuts each curve of other family at right angles in orthogonal sense, right? 90 degrees. So what essentially it means is that a simplistic diagram of it is, suppose you have a family of curves which is like this, some kind of a circular trajectory or something, okay, some kind of a trajectory. You will find that another curve will cut in such a way that it will be 90-degree to this. So if you draw a tangent of from this particular curve, this lines will be at 90 degrees. Okay, so this is a set of straight lines. So these are kind of a circles, I would say. Okay, so this is one of the examples of the orthogonal trajectories. Now, how to find out these orthogonal trajectories? Very simple. You have, suppose dy dx. You find out. So suppose we have dy dx is equal to something, f of x y something. Okay. Now what you do is that you reciprocate it, dx dy. Okay, you calculate dx dy with a negative sign. Find it. Okay, find dx dy with a negative sign. Now, if you see, you will find out that dy dx times dx dy with a minus sign will be equal to minus 1. So, this dy dx, its corresponding y set of curves, and minus dx dy, this corresponding to this x set of curves, or if you say stem y can be found out from here also, y set of curves, this will be at 90 degrees, will be orthogonal. Okay. These are called the orthogonal trajectories. All right. So, what is the physics behind this? What means how we can apply it in the physical sense? in terms of physics. One is that we all know this from the school level physics, also we know that the path of an electric field vector or electric field lines, you can see electric field is always perpendicular to the equipotential surface. Okay, perpendicular to equipotential curves or surface. Okay, this we know. Okay, in terms of fluid also, so in fluid flow, okay, in fluid flow, streamlines and equipotential lines are orthogonal. So there, this kind of theoretical aspect can be applied. Okay, so one example I just wanted to give is one of the examples of this orthogonal set of orthogonal trajectories is suppose you have a differential equation x dy dx is equal to y plus 1. So first thing is that to solve the differential equation, simple. So y plus 1 by x, okay, this we can clearly see that can be solved by variable separable. You don't need the second method, variable separable. So it will be dy upon y plus 1, and here it will be dx by x. Just solve it, you get log of y plus 1 is equal to log of x, and let's see the constant is log of c. So y plus 1 is equal to c times x because log of x plus log of c is log of cx. So y plus 1 is equal to cx. This is nothing but set of straight lines, right? You can see y is equal to mx plus c kind of a thing. All right. Now the next step is what? You make minus dx dy. So what is minus dx dy is nothing but x divided by y plus 1 with a negative sign. Okay. This is your next set of uh, trajectory. All right. So this is your yeah. Okay. So now just do this. In one side, if you just get that is enough. Okay. So now what you will see is that if you solve this, you will get family of circle. Okay, so what you will do is that this minus dx by dy you have done, make it dy dx and solve it. Okay, so you get minus x dx. On the other side, you have y plus 1 dy. Okay, so you convert. Second step is that minus dx dy you see and write it equal to dy dx and then solve it. So what you will get minus x square by 2 plus some c. Okay, and here it will be y square by 2 plus some say c1y. Okay, doesn't matter, it's fine, right? Yes. So finally, you will get uh, yeah something like some x square plus y plus 1 whole square is equal to some c. So what do you get? You get a set of circles, a family of circles. So circles and straight line, they are at perpendicular directions. So set of circles and straight line becoming orthogonal trajectories or orthogonally. Okay, so this is another example. Fine. The next thing is the exact differential equation, and then we will talk about the solutions of differential equation. And the next immediate thing is that some patient differential equations are there, which we will see how to solve. And then we will come to the second order differential equation, where for the week 5 content, we have the solving the homogeneous differential equation. The inhomogeneous one we have to take in the next week's content. Okay. So next we will talk about the exact differential equation. So we will see, just a minute. Okay. So the next is the exact differential equation, right? So exact differential equation. We will see that how you can solve this kind of an equation. We'll see all those things. Okay, so first of all, let us say that you have dy to x is equal to, of course, some function of x comma y. Can be complicated, but see what how I'm writing. See, this f of xy is right. I'm writing it as some p of x comma y divided by some q of x comma y with a negative sign. I'm intentionally putting it. You will see. You will know that how what is the reason behind this. One thing to remember here is that this is not variable separable. In the variable separable, in the numerator, it will be a function of x only. In the denominator, it will be a function of y only. But this is not a variable separable, it is an exact kind of a thing. Okay. Now, if you are writing like this, so finally what you can write, dy dx will be nothing but minus p of x comma y divided by q of x comma y. So you will see that we can write e of x comma y dx plus u of x comma y dy will be equal to 0, right? This equation, this kind of equation, this equation is exact if it is obtained by an exact differential of a function f x comma y. So exact differential is what? This is exact differential. So exact differential. So this is the differential format. So delta f, we know that any total derivative df can be written as in terms of partial derivative times dx delta f by delta y and dy. Okay. Now for exact differential, the df has to be 0. That means, can I write now the p of x comma y is equal to delta f by delta x and q of x comma y as delta f by delta y? We can write. Okay. And finally, if we further differentiate it, so we get delta p delta x should be equal to delta q delta y. Okay. So if you just take the differentiation of delta p delta x, it becomes nothing but delta square f by delta x delta y. Okay. So this is the condition for exact differential equation of order 1, of course. Equation with order 1. So what is actually happening is that delta p by delta y, if I do, I think I have written something wrong here. Yeah, it will be delta p by delta y and this will be delta p by delta x. So how is it happening? So delta p by delta y can be written as delta 2x by delta y delta x Delta Q by delta X is delta 2F by delta X delta Y. And we can flip it delta 2F by delta Y delta X. It's the same, so that's why we can write. Fine. So this is one of the ways to write. Okay. And well, we can prove this that y delta p delta y is equal to delta q delta x. So what we can do is that we can start with the p of x comma y is equal to delta f delta x. Okay, so f will be nothing but p dx plus some g of y. Okay, is a constant of integration, but this constant will be in terms of y. Okay, so from where we are writing this? This we are writing simply just f, just writing this as delta f on one side, p dx on the delta x on the other side. But since this is a partial integration, you will get a constant with y. That is what I am writing. Now, what I am doing is that the gy, you can take the negative sign also, it doesn't matter. So delta delta y of gy will be delta delta y of say p dx, okay, minus some q. Why? Because this will be nothing but delta f by delta y. Okay, so which is nothing but q. Okay, so g of y is now, we can write this as a, okay, fine. Let me write delta y here, and here also you try to integrate with delta y, and you have a p dx. All right, delta delta y of this minus q. Okay, this is what you are having. Delta y goes, this becomes gy, and here you can get, so you, yeah, so it will be delta p by delta y, right, minus delta q by delta. Okay, so this is, I'm sorry, this is one step I have gone through. Let me write it again so that it will be clear. So what it happens is that when you do this and integrate to delta delta y of g of y dy, and on the other side also have dy delta delta y of p dx minus q. Okay, so on the left hand side you have dy, on the right hand side you will be having the same thing, dy delta delta y of p dx minus. Okay, so next thing what we do is that, now if I do delta delta x of delta delta y p dx, okay, so this becomes minus delta q by delta x, right, and this will equal to 0, and this gives you that your delta p delta y minus delta q delta x is equal to 0. From there you can also find out this one. Okay, so this is how you can write. Fine. So this is how one thing can be done. Okay, now let's check about one question about the exact differential equation and how we can use these conditions to solve an exact differential equation. So just you can mention this is the solving exact differential equation. So you have suppose the question 5x4 plus 3x square y square minus 2xy cube dx plus 2x cube y minus 3x square y square minus 5y4 dy equals 0. So can I write this p as 5x4 plus 3x square y square minus 2xy cube? Let's say q, which is 2x cube y minus 3x square y square minus 5y4. Just check the condition delta p by delta y. What is that? Only partial differentiation with respect to y, x being now the constant. Okay, so constant is this will be 0, so it will be 6x square y minus 6xy square. What is delta q by delta x? Is here y will be constant, so 6x square y minus 6xy square. So what we find is delta p by delta y is equal to delta q by delta x. Hence, it is an exact differential equation. Now, how to solve? To solve, you just have to take any one term, say p dx, and you integrate the terms of q not containing x, because I want a function of y z containing x. Okay, so this will be the thing. Okay, so p dx, so you have 5x4 plus 3x square y square minus 2x y cube dx minus 5y to the power 4 dy is equal c. So because this is the only term which is not there, uh, means it not containing x, so we can use this. Finally, if you solve, it becomes 5x to the power 5 by 5 plus 3x cubed by 3 y square minus 2x square by 2 y cube, and this will be minus 5y5 by 5 is equal to c. So all these constants will cancel, and finally you will be left with x to the power 5 plus x cube y square minus x square y cube minus y to the power 5 is equal to c. This is the solution of the exact differential equation. Okay, so the important thing is that the condition is delta p by delta y should be equal to delta q by delta x. If differential equation can be written in this part. This is the important part. Fine. So we have solved each of the things from the start, and we are doing some kind of a numerical question. So that will be a good thing to go ahead. Okay. So next is about the solutions of the linear first order differential equations. Okay. So let me change the color. So this is about the solutions of linear first order differential equations. So one of the important property of those solutions is that so solutions of inhomogeneous ODE, ordinary differential equation, is unique to what? Unique up to an arbitrary multiple of solution of homogeneous OD. So what does it say? So let if say y1 of x and y2 of x be a solution of inhomogeneous ODE. Fine. So what is the inhomogeneous ODE? Linear first order. So dy dx plus px of y. We have seen this is equal to qx. Right. This is the inhomogeneous first order linear differential equation. So say y1 be the solution of this. Right. Then what will happen? It will be just you can just put it over here. P of x y1 is equal to qx. If now y2 is another solution, then we can write dy2 by dx plus px of y2 is equal to qx. Now you subtract it. Okay, subtract. So what we will get? D by dx of y1 minus y2 plus p of x y1 minus y2 is equal to 0. See, this y1 minus y2 is also a solution, right? This is also a solution. But this results into the homogeneous differential equation. So what we are getting is that difference between okay difference between two solutions of inhomogeneous ODE is the solution of corresponding homogeneous ODE. Right? So this is what a result which we are getting. Now about the solutions, the next thing is the linear dependence and independence. So linear dependence of the functions. These functions are nothing but the solutions of ODE. So suppose f1, f2, and so on up to fn be the solutions. Then if we have to prove its linear independence, we know that the simple thing is that you write it in terms of linear combinations, so on up to k and fn, and put that equal to 0. If all k1 is equal to k2 is equal to so on up to kn is equal to 0, then it is linearly independent, right? The same thing can be written in terms of its derivatives. So W, we write it as f1, f2, so on up to fn, f1 dash, first order derivative, so on up to fn dash, or f1 n minus 1 at the derivative. Similarly, f2 dash, f2 n minus 1 at the derivative, fn first derivative, fn n minus 1 at the derivative. In this way, if you write and show that it is not equal to 0, then the functions or the solutions are linearly independent. And this W is called Wronskian in of the functions. Okay, so this is another point. Next is another important part is this is supposed to be the third. This is the linear independence and dependence is the second, and the first we have already seen. The third part is that if first order linear homogeneous ordinary differential equation has only one linear independent solution. So let y1, y2 be two solutions of homogeneous ODE, right? Homogeneous ordinary differential equation, because that is what from where we are starting. So homogeneous ODE, simple, dy dx plus some px of y is equal to 0. This is the homogeneous equation. Now, if y1 is the solution, then we can put it in the, it will satisfy the differential equation. So we can write dy1 by dx plus dx y1 equal to 0. Now, if y2 is also a solution, then dy2 by dx plus px y2 should be equal to 0. Subtract and we get, or we can just write this as 1 by y1 dy1 by dx is nothing but what? Px with a minus sign. Similarly, 1 by y2 dy2 by dx is also minus px. So you can clearly see that a first order linear homogeneous ODE has only one linear independent solution. It can be any of them. So it has one independent solution. Otherwise, it is dependent. One independent solution. Okay. Otherwise, it is dependent because you can see that 1 by 1 dy 1 by dx is nothing but 1 by y2 dy 2 by dx. Okay. So ultimately, if you go ahead with this, you get y1 of x is nothing but some c times y2 of x. That's all. Right? Now, once we have talked about the properties of the solution of the linear first order differential equations, we have talked about three properties about the dependence, linear independence, and dependence. We talked about the homogeneous equations, inhomogeneous equations, everything. Okay. Now is the time to see some special kind of linear first order differential equations and try to solve some questions based on that. Once we do that, we will go towards the different kinds of solutions of second order homogeneous equations with linear equations with constant coefficients. That is the last part of this lecture. Okay, so next we will move to some special differential equations. Just a minute. Okay, so some special first order ODEs, right? So the first special kind is the Bernoulli's equation. So how do you write that? Simple. You have dy dx plus px of y is equal to qx times y to the power. Some kind of a nonlinearity, as you can clearly see, but can be solved. How? You can reduce it into a linear form just by letting z some variables as y to the power 1 minus n. Okay. So what is dz is 1 minus n y to the power 1 minus n minus 1 dy dx. And what is therefore dz by dx can be written as 1 minus n y to the power n dy dx. You can clearly see that some way we are coming into that. So again, if I write the original equation dy dx px of y is equal to qx y to the power n, and I just multiply it by 1 upon y to the power n on both sides. So what you get is p of x, so this will be plus y divided by y to the power n qx, right? Because y to the power n, y to the power n cancel. Okay. Next, what we will do is that, okay, can we just multiply 1 minus n? So okay, 1 minus n y to the power n dy dx plus 1 minus n dx, okay, y upon y to the power n is equal to 1 minus n q of x. So this is known. This is nothing but dz dx. Clear? Plus. Now z is y to the power 1 minus n. So can I write this as z? So yes, 1 minus n p of x is some kind of a constant z times 1 minus n is also a constant. This becomes q of x. Right? Now this becomes again a linear first order ODE. Now you can solve. Okay. Now we can solve it immediately with a question I have. So x dy dx plus y log of y is equal to xy e to the power x. Immediately you will see that okay, y times log of y. This is, come on, this is a product of some function of y with an y. So it comes to some kind of a nonlinearity. But what you can do is that you divide it with xy first, because here you have that, because this should be a function of q of x, right? To have a known kind of a solution. Okay. So what you find is this will be 1 by y dy dx plus y by, sorry, this will be 1 by x log of y, and this is e to the power x. Now this becomes q of x, but here still there is a problem. Now let's check z with log of 1, because ultimately thing you have to remember is that here you must have a dependent variable only, right? Because what is the general form? Dy by dx. This is the general form, or known form, I would say. So this will be p of x y is equal to q of x. So right hand side we have already got some q of x, right? But on the left hand side you don't have only dy dx. Also you have a log of 1. You need some kind of a variable, correct? So I do this, take dz dx. What you will get? It will be 1 by y dy dx. Now we can convert it into known form. So dz dx plus 1 by x and z, this becomes e to the power x. Now it's simple. Just take the integrating factor. What it will be? Exponential of 1 by x dx. That gives you e to the power log of x. Gives you x. Correct? So z times x will be equal to what? E to the power x times x dx plus c. And if you solve it, it gives you zx x e to the power x minus e to the power x. Integration by parts. Plus c. Okay. And what is z? Log y. So x log y will be equal to x e to the power x minus e to the power x plus c. This is the solution. That's all. So this is how your Bernoulli's equation can be solved. Some kind of nonlinearity, but you can reduce it into a linear first order known form of differential equation. Fine. This is one of the things. The second important part is the homogeneous equation. See how to solve a homogeneous equation. Very simple. Suppose you have pxy dx plus qxy dy in this form. Suppose. Okay. Let's look it into a question. X plus y. It's easy to understand. Very easy. Plus or say minus x minus y dy is equal to 0. Can I write dy dx as what it will be? X plus y divided by x minus y? Yes, we can. Now, let's consider y is equal to some v times x. How will you know that it is a homogeneous equation and we can solve it like this? Is that you put y is equal to vx here, x plus vx divided by x minus v. You find this becomes 1 plus v, this becomes 1 minus v. Important thing is that on the right hand side, you will never find any terms of x and y. It will be completely in terms of v. If this is true, then you can go for the homogeneous equation. Okay, but the left hand side should be in the terms of v, right? So we have y is equal to vx. So dy dx will be what? V. I'm sorry. This will be x times dv dx plus v. Correct? Because v is also not a constant. Fine. So you have therefore x dv by dx plus v, that is equal to 1 plus v divided by 1 minus v. All right. So you have x 1 minus v dv dx plus v into 1 minus v is equal to 1 plus v. Okay. So what next is that, okay, let me solve further. X into 1 minus v dv dx will be equal to 1 plus v square. I think I have solved it. Okay, so it will be 1 minus v divided by 1 plus v square is equal to dx by x, and this is dt. Now, okay, so you have to solve it. So it will be 1 upon 1 plus v square dv. This is nothing but some integration. You have to just solve it, dv, and this is dx by x. Correct. So this gives you tan inverse v, which is known form of integral. This becomes, I think, half log of 1 plus v square, and on the right hand side you have log plus comes. So it will be tan inverse. Now v is what? Y by x. So you get tan inverse y by x minus half log of 1 plus y square by x square is equal to log x plus. This is the solution. Okay, so this is the way you should solve. Fine. Okay, we can go for another kind. It is the kind of a second order ordinary differential equation, but can be solved using linear uh, first order differential equation. So this is another third kind. Okay, this is solving a second order ODE and reducing it to first order. Let's see. So suppose you have a question, say d2y by dx2. As you can see, order is 2, x square dy dx whole square. So what you will do? Take z is equal to dy dx. So okay, so you know that dz by dx is nothing but, okay. So dz by dx, you know this will be equal to nothing but the ddx of this, which is nothing but this. So I can write this as x squared and z squared, correct? So dz dx is equal to x squared z squared. Now you can see that you can easily do the variable separately. To dz over z squared, it becomes x squared dx. Integrate it plus c because improper integration. So z to the power minus 2 plus 1 divided by minus 2 plus 1. This becomes x cubed by 3 plus c. So minus 1 by z, x cubed by 3 plus c. So what we will do is that now z becomes dy dx. Okay. So what we can write is that just see for the time being you can uh, I would say that don't consider that. So z is dy dx, which is nothing but minus 3 by x cubed. And finally, we will get y is equal to, again, variable separable technique. So it will be minus 3 by x cubed dx plus c. And so you get minus 3 or plus 3 by 2x square minus 3, something like this. Okay, so this is another form of spatial differential equation. Now, the last part of today's content is the solving of second order linear equation with constant coefficient. So there are three ways. I would say that there are three uh, solutions of different second order linear differential equations, ODEs with constant coefficient. So we will see them one by one. Okay. So the title is now second order, very important, second order homogeneous. Now, by this time, I assume that each and every term's meaning you must know. Yeah? You have known that. Linear ODE with constant coefficient. So with each of the examples, I will give one question and we can solve it. Right? Okay. Second order means something of this kind. d2y by dx2 plus 5 dy dx plus 4y equals 0. You can clearly see the order of the derivative, the highest order of the derivative is 2. That's why it is second order. Homogeneous because it is equal to 0. Linear because no product of uh, the dependent variable and with its own and its derivative is not there. No nonlinear functions present. The degree is 1. Clear? So this is the example of a second order homogeneous linear ODE with constant coefficients. See, this is not a function of x. Important. Okay. So when this kind of equations are there, you how to proceed for solving this. So question is, how do we proceed to solve this? So to solve this, you have a complementary solution. You will see that in the next week lecture that when we will talk about, instead of homogeneous, when we talk about inhomogeneous equation, you will find out that with the complementary solution, you will get a particular integral. That also you have to solve. And how to solve that, we will see that. But the complementary solution, the way we are doing today, same thing we will be applying there also for the inhomogeneous equation. So for the complementary solution, you assume the inhomogeneous equation as the homogeneous equation and then solve it. That's the point. Okay. So let's go one by one. Okay, so so let's take a general. Let us take a general ODE, of course, of second order homogeneous with constant coefficients. So d2y by dx2 with some constant p dy dx plus q y is equal to 0. Right? This is the general. I assume, let us say y is equal to some c times e to the power alpha x. Alpha is also a constant, c is also a constant. If I put it here, then what will happen? You are differentiating it twice, so it will be alpha square, right? C e to the power alpha x plus p times alpha c e to the power alpha x plus q times c e to the power alpha x, because there is no derivative. That should be equal to 0. Great. So now, can I write this alpha square plus p alpha plus q c e to the power alpha x should be equal to 0, or alpha square plus p of alpha plus q into y should be equal to 0. Let's solve this. Okay, solve this part. But this part is also called as the auxiliary equation. Okay, so we will solve this. So how to solve it? Easy. Minus b plus minus root over b square minus 4 c times a, okay, divided by 2 times a. So this is what you have. Now I know that there are three or two kinds of form. One is real roots. I would say three kinds of form: real roots based on the discriminant, and real roots and different roots, right? So three kinds of roots, correct? Real and different. So let us say alpha 1 and alpha 2 be two real but different roots of what? Alpha, correct? Then what will be the solution? Therefore, the solution will be y is equal to c1 e to the power alpha 1 x plus c2 e to the power alpha 2 x. Simple. Second case, if the roots are real but equal, correct? Sometimes happens that we get equal roots, right? There's some alpha. Then your solution will be y is equal to c1 plus c2x e to the power alpha x. And the third, when roots are complex, we will see each of the condition. We will have three questions. We will see that. Okay, it it can happen sometimes when roots are imaginary or complex roots. Better to write it imaginary. Okay, then in that case, y can be written as p1 e to the power iota alpha x or alpha 1x plus p2 e to the power iota alpha 2. Something like that. We'll see. This we will see with example at last. Okay. So each of everything we will have some examples, but generally, actually, what we do is that we write it in terms of like this. So the solution for this is y is equal to a cos alpha x plus b sin alpha. This is what we do. Okay. So let's check one by one. So each of them has three questions. We'll solve those differential equations, try to see how to find out the solutions, and we'll end this particular week's content. Okay. So the first one is d2y by dx2 plus dy dx minus 30y is equal to 0. Check. This is second order? Yes. Linear? Yes. And it's a homogeneous differential equation? Great. And with constant coefficients. Perfect. Everything is fine. Okay. So we assume the starting point is that we assume that the solution y is p times e to the power alpha x. Put that, what you will get? We will alpha square plus alpha minus 30 into y is equal to 0. Solve these auxiliary equations. So alpha square minus alpha minus 30 is equal to 0. We will put this as 0. Y is not 0 because we need the solution of y, right? So alpha becomes minus b. So it will be plus 1 plus minus. I think, okay, this will be plus 1. So minus 1 plus minus root over b square, 1 square minus 4 into 30 into 1. Correct? Divided by. So this will be minus 1 plus minus root over 34 means 120 plus 1, 121 by 2. So alpha comes out to be minus 1 plus minus 11 by 2. So one of the solutions will be minus 1 plus 11, which is 10 by 2. Second solution is minus 1 minus 11, that is minus 12 by 2. So it will be either 5 or minus 6. So let us say alpha 1 is 5 and alpha 2 is minus 6. So there are two solutions instead of one. So then the solution becomes y is equal to from c1 e to the power 5x plus c2 e to the power minus 6. C1, C2 can be find out. So C1, C2 can be found out using initial conditions. If you have two values of x for which y is known, then C1, C2 can be found. Alright, this is one of the questions where the roots are real but different. Let's see another question. And this is corresponding to the second. So d2y by dx2 minus 8 dy dx plus 16y is equal to 0. Again, second order, yes, linear and homogeneous with constant coefficients. Perfect. So let's go ahead again. So let us assume y is equal to c e to the power alpha x. Put that alpha square minus 8 alpha plus 16 times y will be equal to 0. We need a non-trivial solution. So alpha square minus 8 alpha plus 16 should be equal to 0, which is the auxiliary equation. 8 plus minus root over 64 minus 4 into 16, which is 64 by 2. So it will be, so alpha will be nothing but 4, 4. Two solutions, real but equal. So it's a real but equal roots. Then what will be the solution? We have seen that y is equal to c1 plus c2x, directly you write e to the power 4x. This is the solution. Okay. Fine. Okay. The next one is when you have a complex kind of image. So I would say rather say this is an example that why we are writing it as a sign expression. So let's see. d2y by dx2 plus mu square y is equal to 0. Fine. Second order linear homogeneous with constant coefficient and mu is constant. So again, y is equal to c to the power alpha x. Put it in this equation. Alpha square plus mu square y equal to 0. we need non-trivial solution. So alpha square is equal to minus mu square. So alpha will be equal to what? Plus minus iota mu. So imaginary roots. Then what to do? Simple. Just write y is equal to c1 e to the power iota mu x plus c2 e to the power minus iota mu x. Okay. Now e to the power iota x can be written as what? Cos x plus iota sin x. We all know this. So e to the power iota mu x can be written as then what? Cos of mu x plus iota sin of mu x. Similarly, e to the power minus iota mu x will be what? Cos of mu x minus iota sin of mu x. Put that in the equation. Y is equal to C1 cos of mu x plus iota sin of mu x plus C2 cos of mu x minus iota sin of mu x. Done. So if you do this, you can clearly see that C1 plus C2 cos mu x and minus iota or plus iota you can write C1 minus C2 sin mu x. I can take this as some A cos mu x and I can take this as some B sin mu x. That's why we write y is equal to this. And mostly you will see that for the oscillation kind of a feature, this kind of solution is exists. Okay. Now, in an example, mathematical question, let's do and end it. So d2y by dx2 plus 4 dy dx plus 5y is equal to 0. So again, y is equal to c e to the power alpha x. Put that here, alpha square plus 4 alpha plus 5 into y is equal to 0. We need non-trivial solution. So plus 4 alpha plus 5 equal to 0. So alpha will be minus 4 plus minus root over b square 16 minus 4 5 is 20 by 2. So alpha is equal to minus 4 plus minus iota 4 means 2. Okay. So this is what you will get. Okay. So now alpha becomes minus 2 plus minus I. Alright. So y will be equal to C1 e to the power minus 2 plus I x plus C2 e to the power minus 2 minus I x. So clearly you can take e to the power minus 2x common and you have your e to the power I x plus C2 e to the power minus I. And this can be written in terms of sine and cosine. So I'm just not writing anything else. I just write a cos x plus b sin x. This is the solution. So what it represents, this becomes the damping part. Whenever you have an oscillation with some kind of a damping, the damping is given by this. You know this. What is this function? Like this, right? Exponential decay. So this is the damping part, and this is the oscillation part in a physical oscillator. Okay. So I think with this we can end today's lecture. Fine. So what we have started with is about the ordinary differential equation. Okay. We have seen that differential equation are of two types, ODE and PDE. Mostly we are considering ODE here, which consists of derivatives with respect to single independent variable. We talked about order and degree. Then the linear differential equations, what are the conditions for that? And the nonlinear differential equation examples also. We have talked about the homogeneous and inhomogeneous equation. We try to see how to solve linear first order differential equation using when we can write a differential equation in terms of this kind of a format, which is the variable separable format. You can easily integrate it. One of the example is the radioactive decay in physics. We solved one question of this. Next, we try to see the inhomogeneous first order linear differential equation where it has to be solved using integrating factor. We try to solve this. We have solved using some examples. Then the orthogonal trajectories, very important in physical perspective. We have seen that. Next, the exact differential equation. We have seen how to solve and how to check for the exactness. This is the check for the exactness. We have solved this. Next, we came to solutions of the linear first order differential equation where we derive three properties. Next, some special kind of first order linear ODE, Bernoulli's equation. Non-linear equations can be reduced to linear and then solved. So there are three kinds. Homogeneous equation is another, and this is another equation. Finally, the second order homogeneous linear ODE with constant coefficient, which we have to remember. And we have seen that for this homogeneous equation, we need to have the complementary solution. How to do that? Just by assume y is equal to c e to the power alpha x. We need the non-trivial solution and we go and solving. And while solving the auxiliary equations like this, we have three kinds of possible roots. One is that you have real roots, but they are different. Then in that case, the solution becomes this. If roots are real but equal, solution becomes this. And if the roots are imaginary, you can write it in terms of cos and sine. This is physically linked to oscillations. Sine and cos, you can see that it is mostly associated with the oscillations. We solved three examples based on these three solutions of roots. And yeah, we have also seen one example where the damping part is also shown in case of a physical oscillations. So it is kind of some kind of a system like this, which is damping as the time progresses. X is time suppose. Okay, as the X, this is some Y. Okay. So this kind of feature. So it can be damping, you can see clearly, and there is an oscillation also. So this kind of a physical system is also being discussed. Okay. So in the next week, we will be discussing about the inhomogeneous linear second order differential equation. So we will apply the same complementary function, but along with that, there will be some particular integral. And there are some rules to find out these particular integrals. So we will look into that in detail. Okay. So today, I think we can stop. Okay. Thank you very much.